In this video, we discuss learning outcome number 1 of lesson 9.1, which is all about describing the rationale behind the p-value method and critical value method for testing claims about two proportions, and then outlining the basic procedure for hypothesis testing in this case. By the end of this video, my hope is that you can describe the test statistic, describe that distribution of p1 hat minus p2 hat, that you understand what the pooled sample proportion is and what it means and why we're using it, how all of these relate to hypothesis testing. We're not actually going to test any hypotheses using the p-value method or critical value methods in this video. This video is just about understanding what it is we're doing and why we're doing it. And it's going to rely a lot on what we've studied previously about sampling distributions of p-hat sample proportions. Okay, so hypothesis tests about two populations are pretty important. They're very important because often we want to compare two groups. If you've ever heard somebody say, well, men tend to act like this and women tend to act like this, you might say, how do they know that men tend to act like that and women tend to act like that? How do they measure that? How are they able to compare those two groups? They're able to compare those two groups using statistics and probabilities and hypothesis tests, the types of hypothesis tests that we'll be doing in this chapter. Those types of comparisons are very important in research. So this chapter is a particularly important chapter. In our first lesson, we're going to discuss hypothesis tests and confidence intervals involving two proportions. In the next lesson, we're going to talk about confidence intervals and hypothesis tests involving two independent samples and their means. Now, in order to understand what we're doing and why, we need to think about the distribution of p1 hat and p2 hat, or p1 hat minus p2 hat, excuse me. And in order to do that, we need to remember something about the sampling distribution of the sample proportion p hat in general. So we're going to review the sampling distribution of p hat, what that means, and how we come up with the mean and the standard deviation, how those are represented for a particular sampling distribution. And then we're going to discuss the implications for what we know about sampling distributions of p hat for the distribution of this difference between two p hats, p1 hat and p2 hat. And then we're going to discuss the implications of that distribution for hypothesis testing when we're assuming that the null hypothesis is true. Okay, so that's the plan. Let's start by reviewing sampling distributions of p hat. So this is a slide we saw back in chapter 6, dealing with that sampling distribution of p hat, which is a sample proportion. The idea is this: we've got some larger population, and we randomly select n values from that population, and then we compute a sample proportion p hat. And then we select n values again, and we compute another sample proportion p hat. And we select n other values, and we compute another proportion p hat. And we just keep doing this and doing this and doing this. And then we look at the distribution of all of those p hats. And what we said was, under certain conditions, the sample proportions, that distribution of the p hats, tends to be normally distributed. And the mean and standard deviation have very specific forms that we can discuss here. Now, if you wanted the exact sampling distribution, what we would be doing is computing all possible samples of the same size n. And then for every one of those possible samples, we would be computing a p hat, just like we did back in 6.3. So then we're computing the p hats, and then we look at the distribution of the p hats. It turns out that the mean of that sampling distribution of p hat, so that's the expected value of our sample proportion p hat, is actually equal to the population proportion p that we're trying to estimate. That's a very good thing. That's the definition of being an unbiased estimator. So we know that the mean of this distribution is actually giving us exactly what we want. This is targeting what we want, the population proportion p. And then it turns out that the standard deviation of this distribution is equal to the square root of p times q over n, where p is that true population proportion, q is the complement of that, and n is the sample size. And then probabilities that p hat is going to lie in some range are represented by areas under the curve, as we discussed back in 6.3 and when we talked about confidence intervals for population proportions in chapter 7. So here is just a review of the notation that we're going to use whenever we talk about inferences about two proportions. For the first population, we're going to let P sub 1 represent the population proportion. N sub 1 is the sample size for the first sample. X sub 1 is the number of successes in the first sample. P sub 1 hat is the number of successes in the first sample divided by the sample size of the first sample. So it's just the sample proportion for the first sample. And Q sub 1 hat is the complement of that. If you change all those subscripts from 1s to 2s, you get the corresponding population proportion, sample size, number of successes, and sample proportion, and its complement for the second population. So you have all the same variables as before, just double them because we're looking at two populations instead of one. Okay, so now let's talk about how everything that we've just discussed relates to the sampling distribution of the difference between sample proportions P1 hat and P2 hat. Now we talked about the fact that sample proportion P hat tends to have a normal distribution under certain conditions. And we're assuming here that both P1 hat and P2 hat have that property where they are approximately normal. That's actually a binomial distribution that can be well approximated by a normal distribution. Since that's true for both P1 hat and P2 hat, if we take differences between those values, so P1 hat minus P2 hat, that's a new continuous random variable, and that can be approximated by a normal distribution as well. Now it turns out that the mean of the distribution of P1 hat minus P2 hat is just equal to the difference between those two population proportions. So it's equal to P1 minus P2. So if I were to draw a sampling distribution of P1 hat minus P2 hat, the mean would be right here in the middle, and it would be equal to exactly what we want it to be. Now, measures of variation include variance and standard deviation. Now, it's a fact that the variance between differences of two independent random variables is the sum of their variances. Now, I know that sentence has a lot going on in it, excuse me. So let's dissect that. Let's break it down a little bit. So P1 hat is a random variable. It's a continuous random variable. P2 hat is a continuous random variable. So the difference between P1 hat and P2 hat is a continuous random variable. And we're assuming that P1 hat and P2 hat are independent in the sense that those samples are independent from each other. This is saying that the variance of this distribution of P1 hat minus P2 hat is equal to the sum of the variance for the first population and the variance for the second population. So that's that in symbolic form. Well, the variance for the first population is P1 Q1 over N1, and the variance for the second population looks exactly the same, but it has different subscripts. So just applying this fact here, we have the variance of P1 hat minus P2 hat must be equal to this expression over here. Now, I have not proven that to you. I have not described why that is true. I'm just taking it as a fact. We're taking it as known, and then we're getting this result. Now, if I want the standard deviation and I have the variance, then I have to take the square root of both sides. Now, be careful. Don't make the mistake of taking the square root of this piece and this piece separately. You can't do that. All we can do is take the square root of the left-hand side and set that equal to the square root of the right-hand side. And so we get this. So the standard deviation of P1 hat minus P2 hat is equal to the square root of P1 Q1 over N1 plus P2 Q2 over N2. Okay, so now we've talked about sampling distributions for sample proportions and their properties, and how the sampling distributions for sample proportions lead to distributions for differences between two sample proportions. And we know the mean, and we know the expected standard deviation of that difference between two sample proportions. Now that we understand that, we're ready to talk about the procedure for conducting a hypothesis test involving two proportions using the critical value method or the p-value method. First thing we want to do is check the requirements, of for testing a claim about the two proportions. First requirement is that we need to have two simple random samples. The second is that the samples need to be independent from each other. In other words, values from one population are not somehow related to or naturally paired or matched with values from the other population. So we don't want like brothers and sisters. We don't want before and after data. We don't want um, we don't want pairs that are naturally matched. We don't want twins, like one twin in one sample and the other twin in the other sample. These samples need to be completely independent from each other. And then the last requirement is that there must be at least 5 successes and at least 5 failures in each sample. In symbolic form, that can be written this way. Most of the time, I'm not thinking of it in terms of this, though. I'm actually looking at the numbers of successes and failures in each sample. And I'm saying, is that more than 5? Okay, if it is, then we are good to go. Now, as long as that is true, it's appropriate to use a normal approximation to the binomial distribution. If it's not true, then we really should be using the binomial distribution. And that makes a computation, quite a bit more complicated. We can do that, and people often do that, but they use technology rather than doing a lot of computation by hand. But most of the time, we're going to be able to use this normal approximation to the binomial distribution because this third requirement will be satisfied. Okay, so let's say all of the requirements are satisfied. Then whenever we're conducting a hypothesis test, we start as we usually do. We write the claim in symbolic form. We use it to infer what would be true if the claim weren't true. And then we use those two statements to infer the null and alternative hypotheses. And then we either identify the sample proportions and sample sizes from the problem statement or compute the sample proportions and sample sizes from the problem statement or from the samples. Sometimes they give us samples as well. And then this fourth step is something that I'd like for you to do just to emphasize that you understand what it is you're doing and why you're doing it. This is not a necessary step, but I think that if you can include this step in your process, you will begin to understand and begin to retain the ideas that underlie this entire procedure. So we're going to graph a sampling distribution of P1 hat minus P2 hat, assuming that the null hypothesis is true. And then we'll label the sample statistic P1 hat minus P2 hat on the graph. Then we're going to use the assumption that the null is true to compute an appropriate standard deviation in terms of what's called the pooled sample proportion. Now, the fact that the null hypothesis is true has implications for the mean of the sampling distribution of P1 hat minus P2 hat and the standard deviation of that sampling distribution of P1 hat minus P2 hat, or the standard deviation that we're going to use. So we're going to come back to this number 4, but remember, everything that we compute with this test statistic and the p-values and all of that, it's all related back to this sampling distribution of P1 hat minus P2 hat. And then from that, we're going to compute the test statistic z corresponding to the difference P1 hat minus P2 hat. So 4 and 5 kind of go together. That test statistic has a meaning that is related to that sampling distribution of P1 hat minus P2 hat. So before we get into what we would do next, which is either a p-value test or a critical value test, we would be applying the critical value method or the p-value method in order to make a decision about the null hypothesis and then coming up with some conclusion in terms of the original claim. Let's talk about this pooled sample proportion that I just mentioned in number 4. When we assume that the null hypothesis is true, we're going to be assuming that P1 minus P2 is equal to 0. That's the same as saying that P1 is equal to P2. So if we're saying the null is true, we're saying that this difference is 0. So the true population proportion for both samples is the same. So we're assuming that that's true. And then we're looking at the sample statistic P1 hat minus P2 hat. And we're saying, do we have evidence that it's not true? Is there evidence that P1 hat or P1 and P2 actually differ from each other? That's our goal whenever we're running these hypothesis tests, is to say, can we reject this idea that P1 and P2 are equal to each other? But since we're assuming the null hypothesis, excuse me, is true, that's going to have implications for that sampling distribution of P1 hat minus P2 hat that we were looking at a moment ago. Since we're assuming that those population proportions are equal to each other, and our standard deviation involves P1 and P2 and Q1 and Q2, and we're assuming that the populations are equal to each other, we're going to want to estimate P1 and P2 with the same value. Now, we don't actually know what P1 or P2 are, but we are assuming that they're the same whenever we do this hypothesis test. So in order to come up with some estimate of that common value of P1 and P2, we're going to compute what's called the pooled sample proportion P bar. P bar is given by this formula. Now remember, X1 and X2 are the number of successes in each sample, and N1 and N2 are the sample sizes of our two samples. So when we take P bar and we compute it using this formula, basically what we're saying is add all the successes together. How many successes total do we have? If we combine both samples into one large sample, how many successes will we have? And then what would our new sample size be if we combined all of our, if we combined our two samples into one large sample? Compute that proportion of success in the larger sample. That's P bar, and Q bar is the complement of that. I hope that you can see why this would be the best estimate of the common value of P1 and P2. So we don't know what P1 is and we don't know what P2 is. We've got a point estimate P1 hat and P2 hat for P1 and P2, but those are probably going to be different from each other in our in the two populations in our hypothesis test. When we're assuming that the null hypothesis is true, we're assuming that they have a common value. Our best guess to what that common value would be the probability of success sort of in both populations at the same time. So we're thinking of this as a larger population, or excuse me, a larger sample of size N1 plus N2 with X1 plus X2 successes. So I hope that makes sense to you. So we're going to use this pooled sample proportion in our formula for our test statistic Z in order to go from that sampling distribution of the sample, or the sampling distribution of the difference between the population proportions, to the corresponding standard normal distribution. So when we're conducting this hypothesis test, at least in this textbook, we're always going to be assuming that P1 and P2 are equal to each other. In that case, the mean of the distribution of P1 hat minus P2 hat is equal to P1 minus P2. Well, if P1 and P2 are equal to each other, that means we're assuming that the mean of this distribution of P1 hat minus P2 hat is equal to 0. And then as far as our measures of variation are concerned, particularly our standard deviation, remember our variance, the variance of that difference between these two independent random variables is equal to the sum of the variances for each of those random variables. And we got this value over here. But we're now assuming that P1 and P2 are equal to each other. Since we don't actually know that common value of P1 and P2, we're going to assume that the common value of P1 and P2 is equal to this pooled sample proportion, P bar. And then we're going to assume that if P1 and P2 are both equal to P bar, then Q1 and Q2 are both equal to Q bar. So we will replace P1 Q1 and P2 Q2 with P bar Q bar, because we're assuming that P1 and P2 are equal to each other. And the best guess for what those are both equal to, the best guess we have, is that those are equal to P bar. So the standard deviation of this distribution of P1 hat minus P2 hat is approximately equal to this. That's just the square root of this right-hand side of this equation up here, but we're replacing P1 and Q1 and P2 and Q2 with P bar and Q bar. And then again, remember, whenever we are conducting a hypothesis test, the question is this: if the null hypothesis is true, is the value of P1 hat minus P2 hat from our samples significantly high or significantly low? If that difference is significantly high or significantly low, given that the null hypothesis is true, we're going to say, maybe the null hypothesis isn't true. If something is happening in reality that is supposed to be very improbable, but it's actually happening, then maybe the assumption that led us to believe that that was improbable is wrong. That's just the rare event rule. So we'll throw out the null hypothesis, which is typically called rejecting the null hypothesis in that case. Now, if P1 hat minus P2 hat is not significantly high or low, or in other words, it's a value that you might expect to occur due to chance, then we are not going to throw out the null hypothesis. We're not going to reject the null hypothesis. We can't accept the null hypothesis, but we can fail to reject it. We can say we don't have enough evidence to reject this idea that P1 minus P2 might be equal to 0, or alternatively, P1 might be equal to P2. Okay, so we're looking at this distribution of this difference between sample proportions over here. And then we're looking at this P1 hat minus P2 hat, and we're saying, is that significantly high or significantly low? In order to determine whether that P1 hat minus P2 hat is significantly high or significantly low, we're going to convert to the corresponding z-score. Now remember how we computed z-scores way back at the beginning. We took an x value, we subtracted the mean, and we divided by the standard deviation to get a number of standard deviations above or below the mean. That's exactly what we're doing here. We're just using P1 hat minus P2 hat as our continuous random variable. And then the mean of this distribution of P1 hat minus P2 hat is the difference between the actual population proportion P1 and the actual population proportion P2. This P1 minus P2 that we're going to use here is the P1 minus P2 that we're assuming to be true in our null hypothesis. So we're actually going to substitute a 0 here every time, because we're always assuming in the null hypothesis that P1 is equal to P2 when we are testing a claim about the difference between sample proportions in this class. We're always assuming that those guys are equal to each other. And then we'll divide by this estimate of the standard deviation of P1 hat minus P2 hat, which is given by this expression here in the denominator. And that expression involves the P1 or the P bar and the Q bar, because we're assuming P1 and P2 are equal to each other. And our best guess for what P1 and P2 are equal to is that pooled sample proportion P bar. Okay, so we're going to go from here to here, and we're going to say, okay, if this is all true, this is what the sampling distribution of P1 hat minus P2 hat looks like. How many how many standard deviations above or below the mean is that P1 hat minus P2 hat? Is it a lot of standard deviations? A little? What's the probability of getting a z-score or a P1 hat minus P2 hat value that is equal to the value that we have or more extreme than that value? And then we're going to compare that probability to alpha in order to decide what to do about our null hypothesis. Okay, so this is the formula that we're using, and the P1 minus P2 is assumed to be 0 because we're assuming that the null hypothesis is true, and in the null hypothesis, we're assuming that P1 minus P2 is 0. So again, this is the z-score, which is the number of standard deviations that P1 minus P2 hat are above the mean, or above or below the mean, provided that the null is true. And then we're going to make decisions from there. Okay, so after you have graphed that sampling distribution of P1 hat minus P2 hat, or I guess I don't even know if it's appropriate to call it a sampling distribution anymore. We'll just call it a distribution of P1 hat minus P2 hat. Then we can use the p-value method or the critical value method, and you're going to proceed in the same way that you proceeded in earlier sections. So you're going to classify the test as two-tailed, left-tailed, or right-tailed. And then you'll find the p-value using the area associated with that test statistic. So if it's a two-tailed test, you're going to find the area in the nearest tail and double it. If it's a left-tailed test, you're going to find the area to the left of the test statistic. If it's a right-tailed test, you'll find the area to the right of the test statistic. And then you're going to make a decision by comparing that p-value, which is a probability, to our significance level alpha. If p is low, so p is less than or equal to alpha, then that value of the test statistic is significantly high or significantly low. So we're saying that that value of the test statistic is highly improbable, given that our null hypothesis is true. But if it's actually happening, maybe our null hypothesis isn't true. So we're going to reject the null hypothesis. Now, if p is greater than alpha, then that value of the sample statistic that we have from our sample, that's likely to occur due to chance, given our assumption that the null hypothesis is true. So we can't accept the null hypothesis, but at this point we can say, I fail to reject the null hypothesis. And then we can go ahead and state our conclusion about the original claim in non-technical terms. A lot of people don't know what a null hypothesis is, and they definitely don't know what it is to reject the null hypothesis. So talking about the original claim in terms that everyone can understand is the way we want to end any hypothesis test. Okay, so that's the p-value method. Critical value method starts in the same way. We need to decide whether we have a two-tailed test, a left-tailed test, or a right-tailed test. Now, once we decide that, we want to sketch and shade the critical region, which involves finding critical values. So if you've got a significance level of a certain amount, you are going to find the critical value associated with having that area equal to alpha, either in the left tail or the right tail, if it's a left-tailed or right-tailed test, or split into the two tails if it's a two-tailed test. And you'll find the corresponding critical values then there. And then you're going to make a decision. If the test statistic lies in the critical region, then it corresponds to a significantly high or low value of our sample statistic p1 hat minus p2 hat. So if p1 hat minus p2 hat, or if the test statistic corresponding to p1 hat minus p2 hat lies in the critical region, we're going to say that p1 hat minus p2 hat is significantly high or low. So we'll reject the null hypothesis. If the test statistic is not in the critical region, it's sort of in between, if you've got a left tail and a right tail, or if it's just in that sort of typical region for a single-tailed test, then we're not going to reject the null hypothesis. We'll fail to reject the null hypothesis in that case. And then we want to state our conclusion about the original claim in non-technical terms. Okay, so this slide is just a review of everything we've just talked about. We're going to use test statistics, p-values, and critical values, just like we did in chapter 8. The formulas are just a little bit more complicated because we're dealing with two proportions as opposed to just one proportion. And then in the next lesson, we're going to look at two means as opposed to just one mean, but the principles are the same. So we're going to compute a test statistic, and that's going to be a z-score corresponding to p1 hat minus p2 hat. And it will be computed using this formula, and that is a number of standard deviations. It's going to yield a number of standard deviations that p1 hat minus p2 hat is above the mean, or above or below the mean, assuming that the null hypothesis is true. That assumption that the null hypothesis is true affects this value of p1 minus p2 up here, and it also affects that formula for the standard deviation that we're using in the denominator. Since we're assuming that p1 and p2 are equal to each other, that p bar and q bar are being used in our estimated standard deviation in the denominator there. Okay, so you find the test statistic using that formula. The p-value can be provided by technology, or you can use the standard normal distribution table A2. Either one is fine in this case. I would prefer to use technology when possible, because these computations aren't difficult. They're just sort of tedious. They take a really long time. So I will show you how to compute z using technology and compute the corresponding p-value using technology. We can also use the standard normal distribution, and we'll practice doing that too a little bit with table A2, so that you're prepared for solving similar problems on an exam when you wouldn't have access to something like Excel. And then lastly, when you're finding critical values, you're going to use the standard normal distribution as well. So once you decide how much area should be in the tails, and that's always related to your significance level alpha, you can find the corresponding critical values using table A2 or using Excel's equivalent functions to get Z values that go with certain probabilities. Okay, so that is the overview of how we test claims about two proportions using the p-value method and the critical value method. I hope that that makes sense. We talked a lot about sampling distributions of p1 hat minus p2 hat. Please let me know if it doesn't make sense or if I've made a mistake anywhere. I'm relatively new to this material myself, but that's my understanding of what underlies this entire chapter. So I hope this helped you, and I'll see you in the next video to actually apply what we've just studied to testing a claim about two proportions using the p-value method.